Okay, so today I'm gonna talk about Apple One, and I would just cover a little bit of history, and I will tell more about our project, what we do, and some key results that we have already. We will talk about Apple One architecture and our version of Apple One architecture, and then we would go to the building blocks of Apple One that enables you to assemble them and to get an Apple One working like one that Jobs and Woz has. And so at the end would be Q&A, so you can ask any questions. I would love to answer, because we are just we dived really deep in this topic. Okay, so let's start from the beginning. This week we remember that Steve passed away 10 years ago, and it was a great guy who met Steve Wozniak, engineer, the great engineer, and together they made a really great company, and everything started from Apple One. And I talked to Terrell, who is the guy who was the first to believe in this team and who offered them to quit their jobs and to start producing Apple Ones, because he has seen potential that these personal computers could be really popular among ordinary people, not just the business guys or some special institutions. And so he made this offer to them, and they started to build it right in their garage. And fun stuff was that they planned to build it really just like as a DIY kit for just like $40. But he said, no, just please give it the kind of a turnkey and solution, and it would cost $500 each. And they said, whoa, that could be a business. And so let's have our friends together in the garage and assemble it. And so it was like 1976. It was like only the beginning of computing, or personal computing era, and these guys made it all started. And that's why we were so impressed by Apple One, and why we wanted to make it the new version of it, because it started a lot of interesting things. So quick facts about Apple One. Yeah, it was like April 1976. It ran 6502 CPU, which you probably know. And tomorrow, I think it would be Bill Mensch, who was one of the creators of it. This CPU was clocked at 1 megahertz. So it's just, if you for sure would compare it with the modern CPUs, for sure it's not so fast, but for that time, for sure it was a really good result. And the very specific fact about Apple One, that it's text mode only. And it's a very popular question. Could we play some games, like arcade games on Apple One? And for sure you can play something like checkers, or when everything is just scrolled for the new frame. But anyway, it's just text mode with 80 chars by 24 rows. And this for sure, it's like big simplification in its architecture. And as I understand, it was done to make it simpler, to be able to produce it just like a normal time frame. And realizing that was for sure wanted to create Apple II, where it's like everything was just really, graphic system was much more elaborated. So what is SmartyKit? SmartyKit is a kit of chips and the modules and some extra bags that I'm going to show on the next slide. So you get this box, you just like unbox it, and then you assemble it step by step, and in the end you got like really working Apple One. So we have real CPU 6502, we have real chips. We don't have any emulation on the level of logic chips. And we have only Arduinos for video keyboard controllers and for high-res video TV out. So that's it. Everything else is 74 series. So it is a really good tool from our point of view to understand how computers work in general, because it's very simple, it's very basic. and it enables you to just kind of follow all the signals, to check all the data sheets of chips and understand how do they work. And so we also have these beautiful bags inside. So our kit is based on breadboards to enable really newbies in this topic, the guys who are just starting in electronics to work with this. Also, we have these jumper wires. Now we work on the more standardized version with the like standard small, medium, and large wires to simplify assembly, like to make it much more legal style. We have batteries, we have display with the frame, we have electronic components like resistors, capacitors. We have connectors for PS2 keyboard, for connector between CPU and memory, and video out connector, and also video cable for this, because some guys want to connect to their monitors. And we have FTDA cable that is used to update drivers for our Arduino controllers, that is used as video and keyboard controllers. Here's like the render of how it could look when you assemble it. Now we update our instruction and just want to make it beautiful and easy to understand. So we just like model everything right now in 3D. And so it's just like how it looks in 3D for some of the steps. And here how it looks in color and there is real assembled SmartyKit. So what is SmartyKit is a project that we started a few years ago, and recently we've been featured in a video about Apple One by the 8-bit guy. It was really a big thanks to him. It was really cool video, and we have sent him our kit. We presented our kit at CES in Vegas. Guys like Apple Insider, Wired, Italian Version, Cult of Mac, they wrote about us when we were in Vegas and before this. And it's about 100 kits already delivered, mainly to the US and to many European countries. And we have a big backlog of orders and kits and production. That is kind of right now, shippings are not so fast as we wanted, but just like we work on this, we work right now also on logistics. We plan to sign up for a fulfillment center in San Bernardino in California to speed up delivery, and so hope soon that our operations would be much more efficient than they were before. Yeah, here's some pictures, how it was at CES. Also, we presented our concept and kit to Charles Platt, who is the author of best-selling books on basic electronics. Also, we have workshops in the US, in Russia, and in Singapore. And here's a picture from San Jose school where we draw some pixels, learn that pixel is a kind of a 0 or 1 on the screen. And today you also can run our board and to make something like these kids did. So you can draw some kind of a rocket or a smiley or write was name just with 8 by 8 ASCII art. And so yeah, you can do it by yourself. Our board is already there. You could just run it, press reset button, and just upload VOS face, and then you can just type our code from our online drawing tool, and you're gonna see. Yeah, and so a lot of guys from tech, they already have our kits. It's just John Carmack, creator Quake, for sure you know him. Daniel Kotke, one of the first Apple employees. Andrew Bosworth, Facebook VP, you've heard recently about him. They've presented these new glasses. It was his team. And for sure, Steve was our first client and he supported us. He let us use his code in ROMs. So Steve is just like he took part in our webinar describing how Apple One works. So yeah, Steve was for sure the first and the best. Yeah, here's how it looks in real life. I mean, how do people assemble it? So it's a lot of wires for sure. It's a lot of just like testing and yeah, and so you just, but it's fun. It's for us. We think it's just a fun project. Many guys buy it to assemble it with their kids or nephews, or just like a kind of family project, or a gift for their uh, well, for their kids that just like computer science or electrical engineering. Yeah, and you can see we also have this unibody version. I would call it, because it's just like a simplified one, and it's just like one board with batteries, and you just can you can use it on workshops to kind of engage kids, students in learning more about the first computers, about computers at all, electrical engineering, computer science, and we discuss now also with the top tier universities in the US, using it as a kind of a tool to inspire the freshmen and also the guys who study electrical engineering and computer science in more detailed way, because all of the signals could be analyzed by logic analyzers. They could do a lot of interesting experiments with this, and with software, with hardware, and so just like understand how it all works together. Yeah, so let just like take a look at how Apple One in general looks and how it works. Well, from the kind of a helicopter view, I would say that just it looks just like really typical computer, because just everything is done by CPU for sure. It works with memory, where it stores instructions and data to process it, and it needs some in-out modules to communicate with the user. Apple One has very simple communication method. It has just a keyboard that works as a kind of a in serial mode. It sends just one char by char, and displays the same. Displays a kind of a terminal. So just like you send char, you get the signal from display that the next char could be sent, and you send a new one. And so it's it is text mode. It doesn't really work like typical graphic system in a modern computer, when you have like some video memory where every memory cell represents some pixel on the screen, and just you can change this and then refresh screen, and then you frame and you see the new picture. So the main task of CPU or video processor is just to change these memory cells, and then changing the whole scene on the screen. But here it's not. It's very simple one. Yeah, and so the general buses that are there in Apple One is address data, because CPU has like this address to communicate with memory and with in-out modules to address them, and for sure 8-bit data bus that is main highway to transfer everything inside. Here you can see the kind of our version of this architecture. So we just like also made it a kind of level by level. And so in the center, like central module, I would say central level is like CPU level. And here's like, you can see 3 modules. Like the first one is generator on the left. You can run the like also 1 megahertz like it was in the original Apple One. And also we want users to have an option to run it in a slow mode, I would say, to see how everything is working, because we have tests, our own tests written for 6502 that could be run, and you can see how they are executed putting some LEDs into the video port out. So it's really fun. You can see it on our YouTube, like how it's done. So you can switch between these two modes. So CPU module is very straightforward. Just connect the CPU to data bus and address bus. You have a reset button, and you have a sync LED that is emitting when some operation is done. And CPU just like provides two signals, RW, just like read write, and F2, just, and they're decoded into just read and write, separate read and write signals that are used then in ports decoder and in memory module. So decoder is very simple. It's just NAND. So it's like very popular chip, and so also building this kit, you can just like get into details how NAND works. Memory module is ROM and RAM chips. They're together because it's pretty much they have a lot of common pins like address and data. And also we have memory decoder that is just like use A12A15 to decode which memory segment is used, and we're gonna take a look on this a little bit later on the next slides. Also, the in-out is represented by two layers, I would say. The first one is ports layers, and the second is controller layer. On the ports layer, you see like ports decoder that is just like routes for CPU to connect it to one of the physical ports. Here it's like three chips, like keyboard, video, and bit 7 or flex, I would say, port for keyboard and video. That just like helps to work in this char by char mode. And on controller level, it's just two Arduinos in a typical configuration with a crystal, with capacitors, and reset button. And they're just like use drivers from, we have open source drivers on GitHub that is just like work with the display and keyboard. Display is video controller uses SPI bus to connect to display controller or to display, and keyboard. Now we would use our own 40K's custom keyboard, and we're gonna talk about it in more details on when I show it how it looks. So yeah, it's just very straightforward right here. I mean, it's like each level is like, in our case, it's one breadboard, so you can really see it, how it's done. Regarding memory map, in our case, it's 64 kilobytes, and the lower part is RAM, and the higher is ROM. And decoding is done by checking the A15 address line, and if it goes low, so which it generates, it's used to like chip select and output enable for RAM, and for ROM it's a little bit more complicated because we also need a special signal to address our ports, which lay right in the ROM memory address. If there were no any ports in this address space, it would be just very simple. We just need to invert A15 and just connect it to ROM, and that's it. But in our case, we need to use decoder, 3-to-8 decoder, just to connect it to A12, A14, and using A15 as enabling input to work with all these segments one by one. So if we need to connect segment F000, which is the basic one, the first one when that is addressed by CPU when it's just turned on. It is written in microcode inside 6502. So our code, like those monitor simple operating system, should be there. And so the minimum, the very minimum, is to have this one, the signal that will just like routes to chip select and output enable from when F000 is selected. We have electrical scheme also available on GitHub. If you want to just check it after these webinars, you can download it in high res and just like look in more details. But it's pretty much the same. It's like a kind of a sandwich with many layers, kind of a big burger with a lot of ingredients. So you can just like check it and see it. That it's very simple. We have also a lot of capacitors. It's like decoupling ones, just to make this power more stable, as you probably know. Yeah, okay. Well, what are the building blocks? What are just like these bricks, Lego bricks that you really use to build your own Apple One? So in our case, is just for CPU, it would be WDC6502. The one that is produced by Bill mentioned his company. So we use them. It's very good that it's CPU, it's static, so it just like can stop at any clock, and just like it's simple, it's a single step and so on. And we use this crystal generator like for 1 megahertz and 555 for low rate clock, and also we use this NAND gate to decode a read-write signal. For memory, we use 65.256. For ROM, we use like 65 kilo ROM to make it simpler when you program it, because for sure we can use 32 kilos for ROM, but in this case, if you write some program, you assemble it, you compile it, and you got this machine code with some addresses. If you're gonna load them in this ROM, you just wouldn't see the exact addresses, because right now you can edit segment FF00, and you just like it would be right the same addresses as CPU reads them. If we would use 32 kilos chip, it would be much harder to program it and understand it, which is like with this relative addressing mode. For 328 decoder, we use 138. Is just also classic, the really classical one, and for this we use like 3 inputs for A12, A13, A14, and A15 is used like the enabling one. Because if A15 is goes low, in this case, this memory decoder would output everything high, and so it would mean that ROM would not be selected when the RAM is addressed. Output ports. In out ports, we have like this out port is latch register as a video port, because when I want to latch char code, ASCII code of char that needs to be sent to display. We also use either register, just simple register for a keyboard port, either shift register to simplify connection to make it serial, not just parallel. And we're gonna discuss it when I take a look at our keyboard. We use a buffer just that with output enabled pins for the bit sound port. When it's addressed, it just like transfers the flag pin from video or keyboard controllers right to the D7 data bus pin. And we use this 4 to 18 decoder as ports decoder, where we, just like as inputs, we have two lower addresses like A0, A1 to address ports, because they all like have numbers like D10, D11, D12. And also we add read and write signals to combine them to have signals that specifically read some port or write to some port. And just like it is easier to have this decoder instead of some extra logic to make some ORs or NANDs or ANDs or some logical operations for signals. We do everything right inside this decoder. Regarding controllers, it's just Arduinos with this just using classical, I would say, code to work with the video controller, but we needed to make it speed up it, so we have used the basic driver for such a displays, but we needed to put everything in one file and to speed up this SPI connection to speed up the scrolling, because basic scrolling was very wasn't very fast, and we need to work with this because otherwise it looked really strange. Keyboard controller can work in two modes, I would say, with the two versions of drivers. One is for PS2 keyboard. It supports it. It's a very simple one. And the second is our own 40 keys keyboard, where it needs to do much more work, because it needs to scan all this keyboard to find the key that was pressed, and then using the table decode it to ASCII code, and then send it to keyboard port, and then CPU can read it. Display is just like assembled from a standard one, but we need to convert it to 3.3 volts, so that's why we need a lot of resistors, and so we use special module to do this. And also it has frame to look nice, because in basic it has red color. It doesn't really look cool when it's red. So it supports this text mode. It has scrolling, and also basically it supports also touch screen. We have experiments with a touch keyboard, but many users with whom we discussed this, they said that it's cool, but kind of it's not really Apple One spirit to have a touch screen keyboard. So it's better to have real keys, and we have one. Yeah, so we created this one. Now we kind of updated it a little bit to support for this automatic production with the SMT, and but it's pretty much like this. So it's 4 rows, 10 columns, and keyboard controller needs to scan this rows or columns. It doesn't really matter. It's just like how you do it. But anyway, you just like need to scan 0 or 1 and check in which row and which column key was pressed. Then you need to check shift if it was pressed too. You need to save it, and then you use table to convert the kind of it's kind of index in array, so you convert it to ASCII code to send it to CPU, because CPU for sure and it works with the ASCII codes. And yeah, it was kind of fast, but it's pretty much how it works and how it what we do. So would love to answer your questions.
Do you want me to ask him? All right, Sergey, we have a question.
Sure.
can you put this in an empty Apple II case
Yeah.
and use the keyboard?
You can put it inside the empty Apple II case and connecting keyboard. Because as I remember, Apple II doesn't, it's like it has a built-in keyboard like an Apple One, and so it uses the special connection, doesn't have any PS2 interface. So in order to do this, you probably would need to have some converter that could be used to use it as a kind of a keyboard for SmartyKit.
Okay, yeah, that makes sense. It's not straightforward. It's a little complicated. Okay, makes sense. Does anybody else have any other questions for Sergey? Yes. Are there any extra features that you get by using new parts as opposed to original vintage parts? Any new features?
Yeah, sure. Yeah, I mean, basically, we use like one RAM chip. It's much simpler. I mean, when you do assembly and the cool stuff about, for example, video and keyboard controllers, that now you can just like have it kind of as a, I would say, laptop. Because you have like display right on the board, you have keyboard just like stick together. So it's a new feature, I would say. You can just like have your have it portable. The original Apple One is just like, you know, it's a keyboard and the big monitor that you can transfer it, but it's just you need a kind of a power supply. In our case, you just need batteries. And also, what's cool. And what, yeah, because mainly what we use as new ones is just these controllers and one memory chip to simplify everything, and the rest is like it's original. I mean the 674 series for all the logic, original CPU. The new version of it, I mean, with the static mode, so you can just like, as I've said, the main feature that you can run it at low clock or stop it, just like making step by step, which is cool for education. And the rest is like very genuine, I would say, and it has the features of original Apple One, I would say.
All right. Any more questions? Yes. What are the inputs in for it? So it's like the original Apple One. What are the inputs for it? Or is there, like, to put a program? Does it have a cassette port, for example?
Yeah. In our case, right now, it's like we have like built-in programs, right, in RAM, like this pixel art and some Hello World programs. For sure, can burn some classic software like BASIC right to the RAM using programmer. Yeah, we tried to make a kind of a serial interface from computer, so you can just like emulate key by key pressing of the keyboard and just like repeating the code, was monitor code, I mean, to populating memory cells. But right now we don't really support this. We just use built-in programs. We can support this in a keyboard driver, so we can open Arduino development program and then just change the code to burn it to as a part of a driver, and then when you press, for example, tab that button, it just like would load it also char by char this program that you want to have. So we have questions here about this cassette interface. For sure, it's possible because it has all the signals. It has this memory decoder that addresses C000 memory segment that was used for cassette interface. But I would say it's a kind of a special challenge for guys who would love to have this. It's possible. It's not. I know even now I understand how I can do it, but we have much more questions about the assembly of this one. I mean, to run VOSFace program, for example, and stuff like this. And so we're just like focused, spend our time on making our instruction look like a legal one. They can sit and do it much more than developing this cassette interface. So I think we're gonna make maybe some challenge, or I would say a kind of a hackathon to guys who would love to compete in making something like this. I would say to have this cassette interface.
Okay. Are there any more questions? All right. Looks like that's all the questions, Sergey. I appreciate it.
Okay. Thank you.
You're welcome. Thank you for showing this. It's very interesting.
Thank you, guys. Yes. So please follow us, subscribe to our email list, clone our code at GitHub, and for sure watch our videos on YouTube. Would appreciate that. If you can drop me a line if you want to know something special, or just say thank you. Well, just please do it. Drop me a line. I would appreciate this. Yeah, for sure. It would be cool if you could run it and share some pictures. Yeah, how you do it, because it should be simple. I mean, you just like turn it on with a switch on top right. It start printing like Made with Love by SmartyKit.
On. Oh, yeah.
Then you press reset.
It's showing Wozniak.
Yeah,
it's
we got it.
The Apple, what is it, 30th anniversary demo?
Yeah.
Oh, there you
that's
go.
it.
I didn't see that before. That's pretty cool. And then it'll just cycle through the different ASCII art of Wozniak and then Jobs. All right, I've seen that before. Okay, that's pretty cool. All right.
Yeah.
I'll let them see that if they want to. Thank you, Sergey.
Thank you.
All right. Have a good day.
Yeah, thank you, guys. Have fun there.